All right, good morning. And I hope you guys are doing well. I hope we'll see what happens regarding. I haven't heard anything from the school administration regarding what's going to happen next week. So I have just as much information as you. Um, I don't know. So again, the plan is if classes will be in person on Monday, we will take the midterm exam on Monday at 8 a.m. And that will be the case. If they cancel classes before 8 a.m. Monday, then if they cancel just Monday's classes, we'll delay it to Wednesday, and then if they cancel Wednesday's classes, then we'll just cancel the midterm entirely. But that's the plan. And we'll see what happens. I've posted homework 4. I apologize for the delay in getting that up. I've extended the deadline for homework 4 to Monday, May 20th. So homework 4 is up there, and it was originally going to be due Friday, May 17, but we'll make it due Monday, May 20th. Okay, let's take a look at our lecture. We left off on Wednesday, and we discussed the Bayes classifier, and we have now I want to cover a Bayes classifier for a mixture of multivariate Gaussian distributions. Okay, so the idea here is we have multivariate Gaussians. Okay, this is the PDF for the kind of multivariate normal distribution. And basically it's the kind of a higher dimensional generalization of the normal distribution. And so I'm going to generate some random multivariate normal data using the library MVT-norm. So this is a package. You might have to install it, but this allows you to generate random multivariate normal values, and there are a few useful kind of functions there. There's D MV norm to get your density, and then you have R MV norm to generate random values. And so in order to generate random values, we have you need to create a mu vector, and then you need to create a sigma matrix. So I'm going to have 3 different kind of distributions, and each of them we're going to have 30 values from each distribution. So I have one distribution centered at the coordinate 2, 3, and its sigma matrix is 3, 0, 0, 1. Okay, so you've got no covariance. They are independent. The off diagonals are 0. Then we have mixture B centered at 0, 0, and its sigma matrix is 1, 0, 0, 1, the identity. And then we have mixture C, or distribution C, which is centered at 2, -2, and its sigma matrix is 3, 2.5, 2.53. So there is covariance between x1 and x2 for distribution C. And so we have these points, and then we're gonna bind them all together into one big matrix with 90 rows, because we're generating 30 points from distribution A, 30 from distribution B, and 30 from distribution C. So the result of RMV norm is going to be 30 rows and 2 columns. The result for this is also going to be 30 rows, 2 columns. And so when we bind all of these together, we're going to get 90 rows and 2 columns. And this is just some commands to plot it. We're basically going to plot XA in red, okay? and then we'll plot XB in blue and XC in green. So each of our points in red, blue, and green. And then these are just to kind of set the things. And then here I'm drawing ellipses. And I'm drawing ellipses at the 40th percentile, 65th percentile, 80th, 90th, and 95th percentiles. And so so the ellipses look kind of like this. This is to show you what the normal distributions look like. So these ellipses reflect the known distributions where the center is at 2, 3, and we have, you know, sigma matrix 3, 0, 0, 1. Okay, so here you can see because we have 3, 0, 0, 1, that means the x1 direction, your variance is 3, and in the x2 direction, your variance is 1, and there's no covariance. So the major and minor axes of the ellipse are perpendicular. The center of this thing is at 2, 3. So we have 2 is right here, and then the center of the ellipse is 2, 3. Here's this thing. They end up being concentric circles, the center being 0, 0, and the variance in the x1 direction is 1. The variance in the x2 direction is 1. They're perpendicular to each other. Here, the center of this ellipse is 2, -2. And we the variance in the x1 direction is 3. The variance in the x2 direction is 3. And there's covariance of 2.5 between them. So these black lines represent the known, I guess, properties of these distributions that we've simulated. Okay. So it's important to recognize that because we generated the data, we know exactly where the center should be and what our kind of our sigma matrices should look like. Okay, but in reality, when you have a classification problem, all you get to see are the dots. Okay, you only get to see, you have red dots and blue dots and green dots, or you get to see you have dots in these, you know, coming from these different classifications. But you don't actually, you probably don't know what the mean and variance is for any of these distributions. So we have to estimate these, okay? So what we would do to estimate the mean is we just take the mean of the observed data, right? So here I've got 30 points in red, and I'm going to just take the centroid of those 30 points. Here I've got 30 points in blue, and I'm going to take the centroid of those blue points. And I've got 30 points in green, and I'll take the centroid of those green points. And you know, as far as a formula goes, that's just going to be the sum of your x values divided by how many values you have in that particular class. So we will add up our 30 points. You know, as far as the matrix computation goes, you think of all of your red points, and you're going to have 30 rows and 2 columns. And basically, you just take the mean of column 1 and you take the mean of column 2. So you've got, you're going to take the mean of the 30 x1 values and the mean of the 30 x2 values for red. Same thing for blue, same thing for green. And you get the mean there, okay? So I can just say, hey, give me column means for the values in XA, give me the column means for the values in XB, give me the column means and the values for XC. And these are going to be the estimates of my of the mean for each of these things. And so you can see they're kind of close, but not exactly close. They're not exactly the same as the true value. So the true mean that we use to generate the points for cluster A, its true mean was 2, 3, and our mean is what? Our estimated mean is 2.26 and 2.82. And the true value for cluster B should be 0, 0, and we're getting 0.3 and negative 0.1. And the true means for cluster C is 2.22, negative 2, and we're getting something around 2.25 and negative 1.9. So, you know, kind of close, but not exactly. The variance matrix, okay, for do you call it? For our points is going to be basically you take the difference between each observation and the mean, so x minus mu, and you would do this for everything. Each point, x minus mu times x minus mu transpose, that's going to give you a 2 by 2 matrix. And then you get that for every single dot, and you add them all up and you divide by n. That's going to give you your maximum likelihood estimate. This is assuming your observation is a sample drawn from the population. This is going to be biased, right? If you want unbiased, you divide by n minus 1 rather than n. But this will give you slightly biased estimates. That's okay. And if you want to get rid of the summation, you can actually just kind of deal with the entire X matrix, and then you do all of X minus mu transpose times X minus mu. I guess you'd have to broadcast the mu or recycle the mu to do X minus mu appropriately, okay? These are going to give you biased estimates of the variance. So if you want unbiased ones, you divide by n minus 1 rather than n. And this is actually what R would generate if you ask for, give me the variance of a matrix with 2 columns. So if you have 30 rows and 2 columns and you say, hey, give me the variance of this matrix, it's going to use this formula and give you a 2 by 2 matrix. So you can just, so here I asked, what is XA? XA is 30 by 2, 30 rows, 2 columns. And n sub a will be 30. And here, the variance of XA is going to be this 2 by 2 matrix. The variance of XB is this 2 by 2 matrix. And the variance of XC is going to be this 2 by 2 matrix. And the true values, I think, were 3, 0, 0, 1. And the true values that we used to generate were 1, 0, 0, 1. And so we're getting, again, kind of close, but not exactly. And I think this one's kind of the one that's the most off. I think it was 3, 2.5, 2.53. And, for whatever reason, we're not seeing as much variance in this cluster. So anyway, these are the estimates of the variances of our data. And we can kind of plot those, all right? And so if you plot the ellipses, this reflects the estimated means and the estimated kind of variances as shown by ellipses here, okay? And so these ellipses are drawn with like these different centers and things like that. So I've overlaid, can you guys see the orange lines okay? So the black lines represent the true centers that we used to generate it. So when we generated our points, we used RMB norm. And because it's random, we didn't get values that are like perfectly, like if you look at these blue dots, okay, they should have been generated centered at 0, 0 with this variance and covariance, but you can see just by random chance, the blue dots that we generated aren't exactly centered among these circles. And so this, if we say, hey, fit, basically estimate the mean and variance based on the dots generated, then the corresponding ellipses that appear are shown in orange here, right? These are the mean and variance that we've estimated from the dots that we've generated, okay? And they are slightly different from kind of the distribution that was used to generate the dots, okay? And the same kind of thing happens with, the red dots and the green dots. These are the ellipses. This is the ellipse that we would estimate based on the actual dots that we have versus, when we generated the dots, we were expecting something a little bit different, okay? And so what we want to do now is we want to do the Bayes classifier. And so for the Bayes classifier, here is going to be a test point right here. I'm going to put it at 0, 0. And I'm going to ask, if this is our test case, can we guess what class it belongs to? Is this, if we notice a dot at 0, 0, should it belong to the red class, the blue class, or the green class? Okay. And I think it's obvious. If it's right here, we're going to say it's most likely a blue dot. Okay. And so we're going to do the Bayes classifier for that. Okay. So let me switch. I think we'll switch to our lecture slides over here. So yeah, this is where we are. Okay. So here's the dot right here, 0, 0. And we want to say which class does it belong to? Does it belong to red, blue, or green? And so looking at this, I think we would say, oh yeah, that should be blue. Okay, that should be class B. And so how do we go about calculating this? We are going to use the Bayes classifier. Oh, you know what? Before I forget, our first view quiz answer is the letter B. B as in bear. So we're going to use the Bayes classifier. We're going to say, hey, what is the likelihood of this data point? And we're going to multiply it by the prior probability, and we'll divide it by the marginal probability. Okay. The likelihood is going to be calculated by saying, all right, what is the probability of generating, or what is the likelihood of generating this point 0, 0 if it came from the red class? What's the probability of it generating 0, 0 if it came from the blue class? What's the probability of generating 0, 0 if it came from the green class? Okay, that's what we want. And so we can calculate this using the density function of the multivariate normal. And we will say, all right, here my x observation is 0, 0. And I would do 1 divided by 2 times pi raised to the 2/2, d being 2 dimensions, times the determinant of the variance matrix of, so here we're going to do it for A, class A, the red class, raised to the point negative, raised to the 1/2, times e to the negative 1/2 times x minus the mean of A transpose times the inverse of the variance of A times x minus the mean of A. All right, I'm just using the exact PDF here in R, and I get this number 0.000879. Okay, this is fine. Luckily for us, there is the function with the multivariate normal package. We can just do DMV norm. This says, give me the density of the multivariate normal. I want the density of my new point, x underscore new, 0, 0. And the mean is going to be the mean of A, x bar A. And the sigma matrix is going to be the variance of A. So remember, we estimated these using the data points that we've observed. We had 30 red dots. And we said, hey, what is the mean of those 30 red dots? That's x bar A. And what's the variance of that 30 by 2 matrix, and we got a 2 by 2 square matrix for the variance, and we plug that in. And when you plug that in, we get the exact same value, 0.000879539. So so I could do the long old-fashioned way of using the PDF of the normal distribution. I can also just use DMV norm. So I think DMV norm, I think this is easier to read and understand. We just know that this is the density of the multivariate normal. So that's what we'll use. Okay, we've got, we do that for class A. We're going to plug in 0, 0 for class B. And the density there is 0.1654. And then we plug in 0, 0, and we say, hey, what's the likelihood that, what's the density of generating that 0.0, if it came from class C. And that's a really small probability. Okay, the density there is 1.6 times 10 to the negative 5. So really low density there. Okay, the prior probability is the probability that our test case kind of belongs to either class A or class B or class C before you know anything else about it. And so we will use our prior probabilities. We're going to estimate that based on basically how many points we have observed, right? So in our case, we've observed 30 from class A, 30 from class B, 30 from class C. And so right now my prior probabilities is that class A and class B and class C all have kind of the same probabilities. So we've got the prior for A and the prior for B and the prior for C. We'll all just do 1/3. Okay, that will be our prior probabilities, is that each of them have a probability of 1/3. And then so the marginal is we take the marginal, we take the numerator, which is the likelihood times the prior, and we will multiply it for we'll multiply the likelihood times the prior, and we'll add them up for all of the possible classes. So we do it for class A, likelihood times the prior, plus we do the likelihood times the prior for class B, and we do the likelihood times the prior for class C. Okay, and that will give us the marginal probability. Okay, and so when you do that, this ends up being our results, our posterior probabilities, as we do, the likelihood times the prior divided by the marginal. Likelihood times the prior divided by the marginal, and the likelihood times the prior divided by the marginal. Now, technically, because the prior ended up being exactly the same for all three classes, 1/3, 1/3, 1/3, I could have just kind of skipped that, and I could have just done the sum of the likelihoods divided and used that as the marginal, because they would have been kind of proportional, but it doesn't matter. We did likelihood times the prior of 1/3 divided by the marginal likelihood. And so what we end up getting is around 0.005, 1/2 of 1% for class A, 99.5% for class B, and then something very close to 0 for class C. Okay, 9, so basically 10 to the almost -4 here. So around 1 in 10,000 for class C. So kind of going back at our picture, that aligns, right? So when we look at this dot right here, we're going to say, yeah, you know what? It makes sense that it came from class B, the blue class, with the highest probability. What's the likelihood that it came from class A? Not super great, okay? Pretty low, but it's even lower for class C, the green dots, because the green dots centered here, you've got this kind of covariance, and so to end up way out here at 0,0 is really, really, really unlikely. And so therefore its probability is around 10 to the -4, 1 in 10,000, whereas much higher probability for 0,0. Is that okay as far as arriving at these numbers? Here, we'll try another case. This one's at 6,2. So if I go to 6,2 and I ask for what is the probability here, just kind of eyeballing it, which one do you think has the highest likelihood or has the highest posterior probability? Which class? If you had to put these in order from highest probability to lowest probability. Class A has the highest, yep. And then C being the green ones next, and then least likely to come from B, right? If B is centered over here at 0, 0. So yeah, let's see if we do that. Okay, so we'll go ahead. And so I calculate the likelihood using DMV norm. This point, the new point is at 6, 2. We'll calculate the likelihood. The priors are all 1/3. The marginal is the likelihood times the prior, and we add them up for all 3 classes. And then we'll get the posterior probability by doing the likelihood times the prior divided by marginal. And so when we do this, we get around 79% for class A and around 20.5% for class C. Yeah, 79.5 for A, 20.5 for class C. And this for class B is 3.3 times 10 to the -9. So that one has the lowest probability by far the lowest probability. And so yeah, around 80, close to 80%, 20%, and practically 0. Okay, for class A. All right, here's another one. Here I put a dot right here, 5, 1. And so looking at this, it looks like fairly close probabilities for class A and class C. Maybe a slight preference for class C over class A. Still almost no probability for class B. Okay. So when we do this, we get, again, we calculate the densities for class A, B, and C. And then we get 39% class A, around 61% for class C, and then again, something close to 0, 7.9 times 10 to the -6 for class B. So this one, a slight favoritism towards class C, 39 versus 61. Okay, here's a point. I try to pick one kind of in the middle of all of them. And when you do this, we get around 30%. This is 2.53, 0.37. And we get around a 30.6% for class A, 36% for class B, and 33% for class C. Okay, so that's what we end up getting. Okay. But yeah, all 3 have similar values. So again, we're just doing the Bayes classifier, and we calculate it using the likelihood. The likelihood is, hey, what is the probability of getting this location, using kind of the estimated, using the estimated values of the distribution. So if, we estimate what is the mean of the distribution, what is the variance of that distribution, and using those values, what is the probability of getting this point? That's the likelihood. The prior probabilities are found using kind of what do you call it? The counts. And so, in our case, we had 30 from each class. And so because we had 30 from each class, our priors all ended up being the same of 1/3, 1/3, 1/3. And I think the marbles from the factories problem, we had different counts. Half of the bags, 12 out of 24, came from factory A, and 6 came from factory B, and 6 came from factory C. So using that, we got different prior probabilities. And then we can you calculate the marginal by doing the likelihood times the prior, adding them up for all the possible classes. Okay, let me give you your second view quiz answer. The letter E as in elephant, is your second answer. Okay, let's do the naive Bayes classifier. Okay, so the naive Bayes classifier is very similar to the Bayes classifier. The difference here, though, is that we will assume that all of the x variables are independent of each other. Okay, so that's probably a bad assumption. Okay, but by kind of just making this bad assumption that all of the x variables are independent of each other, you can actually get a more useful model, because the reason being is that to estimate, if you don't assume the x variables are independent, you have to estimate the covariances. Okay, and And estimating the covariance between your variables could become really, really, really hard if you have a whole bunch of X variables. You might need like a ton of data. And so trying to estimate the covariance between all of these variables can end up being quite challenging, okay? So we'll first revisit the mixture of Gaussians, and then I'll just show you another example where this naive assumption is actually going to be pretty helpful, okay? So on the left, I have the multivariate normal, okay? And this takes into account kind of your sigma matrix, all right? And I think if you go back to an earlier lecture where I kind of talk about the multivariate normal distribution, I showed that if you have zeros on the off diagonals, if your covariance matrix sigma is a diagonal matrix, then you can factor out the multivariate normal distribution into a product of univariate distributions. Okay, you can have just the normal distribution for one X variable at a time. And if you just have a diagonal matrix sigma, you can show that these two are equivalent, right? So if we assume there's no covariance between any of the X variables, then the multivariate normal distribution can be factored down into a product of univariate normal densities. And so here's kind of the simulated data before. This is what it would look like. This time we can estimate the mean and the variance of these things. For the variance, though, we're going to estimate the variance and the standard deviation just one variable at a time. So I'm going to just look at column 1 of XA and get the standard deviation. And then I'll look at column 1 of XB and get the standard deviation, column 1 of XC and get the standard deviation. I'll look at column 2 of XA and get the standard deviation, column X2 and get the standard deviation, and so on and so forth. And so if I plot kind of the corresponding ellipses there, we don't see a huge difference for the red and blue because we had already assumed those were independent, but we see a big difference for the green because now we're assuming there's no covariance. Okay, no covariance between X1 and X2 for the green dots, which is wrong, right? There's high covariance, and here we're assuming that there's no covariance. Okay, so you know our values are going to be quite a bit different, especially for the green dots, in that we're assuming there's no covariance there. But as far as the calculation goes, it follows the same process. Okay, here I'm going to put in a test case at 0, 0, and we're going to say, hey, is it going to come from blue, red, or green? And we go through our calculations. We're going to do our likelihood times the prior divided by the marginal. Okay. The key difference here is for the likelihood, we're not going to use the multivariate normal density. We're going to use the d norm, just the regular old normal density for variable 1 times normal density for variable 2 times normal density. Well, I guess there's only 2 variables here. But if you had multiple variables, you're not going to have any kind of covariance there. You're going to just calculate the multivariate normal density. And you're not going to calculate the multivariate normal density. You're going to calculate the normal density one at a time, one variable at a time, and take the product of them. Okay, so we're going to take the product of independent normal density functions for the likelihood. Prior marginal found the same way. So here, the likelihood of point A is we're going to take in our new point, x new, the first value, 0. It's 0, 0. So we're going to just do the first 0 at the x1. And then we're going to say, hey, get the mean of x of A, and then the standard deviation of x1 for class A. And then we do it for the second observation, okay? And not the second observation, the x2 value. right? So x2 is also 0. We're going to get what's the mean of x2 for class A? What's the standard deviation of x2 for class A, right? One thing to remember is in R, the density function for the normal, the PDF, normal PDF is the density function, that's d norm. Do not use p norm. P norm is the cumulative distribution function, CDF. We want the probability density function, the PDF, that's d norm. So you have d norm, we're going to do it for x1 and x2. We do d norm for x1 and x2, but this time for class B. And then we do d norm for x1 and x2, but this time for class C. And these are our numbers, 0.00128, 0.163, 0.0094. And we get our priors, they're all 1/3. Marginals, likelihood times the prior for all three classes. And then so our posterior probabilities is the likelihood times the prior divided by the marginal. I get something, 0.007 for class B, 0.938, and for class C, 0.0539. So the probabilities of class A and class C are kind of wrong, but still we get the highest probability is that it belongs to class B. Okay. So that's the naive Bayes classifier, is that we just assume everything is independent. X1 and X2 are independent of each other. And it gives us pretty good results still, okay? Obviously, in some cases where assuming it's independent is a very bad assumption, your results are going to be wrong. But here I'd say it's overall it's still okay. It's still okay. All right, here's an application of the naive Bayes classifier. Is we could do something like document classification. Okay. The document classifier, the reason why the naive Bayes classifier here is useful is that your variables are going to be counts of words. How many times did this word appear? How many times did this word appear? How many times did this word appear? And if it wasn't the naive Bayes classifier, you're going to have to calculate the covariance between a whole bunch of words, okay? So certain words are more likely to appear together. Like here I have White House. That's a thing. And so if you think about words that appear together, yeah, White House kind of is going to have a higher probability. Red light. So some words have higher probabilities of appearing together, but if you had to figure out what is the covariance between all of these different words, what's the covariance between the word bed and pillow, and what's the covariance between the word bed and I don't know, tennis, okay, or computer, like it's going to be really tough because, let's say you have a vocabulary, I don't know, let's keep it simple. Just say there's 10,000 words. You have to find all of the covariances between this word and the 9,999 other words, and then the next word and the covariance between that and all the other words. And so there's going to be a ton of covariances to figure out, and it might be impossible to calculate those covariances without a giant database. Okay. So here we're going to just say, you know what? No covariances. I'm not going to worry about any of those covariances. We're going to just treat all of the words as independent. Okay. We're going to use a bag of words model for the document classifier. And basically, the only thing that matters in a bag of words model is the count of the words. So, you just imagine you have some kind of, I don't know, some kind of document with words on it. I don't have that. Okay. So just imagine, like in a cartoon, okay, you have a document with words on it, and then, in a cartoon, like they shake the paper and then the words fall off from the paper, okay? And then you catch them in a bag. All right. So you've lost the structure. You've lost the order of the words. Okay. but you still have the words themselves, and so you can get a count of the words. That's the bag of words model. Bag of words model does have some severe weaknesses, like because the word order doesn't matter, these two, quote, documents is just a collection of words that, this thing that you're trying to classify would end up having the same analysis here, right? So if the document says it is bad, it is not good, when you do it into bag of words, you say, well, it appears twice, is appears twice, bad appears once, not appears once, good appears once. Okay. This other document, it is good, it is not bad, is going to have the exact same counts. It appears twice, is appears twice, bad appears once, not appears once, good appears once. Okay. And so a bag of words model, is whatever score it gives this is going to give it the exact same score to this, even though these two things have opposite meanings. Okay. They're going to have, because they have the same word counts. So then, severely limited as far as what the bag of words model can do. But it's still, you can still do some useful things with it. But yeah. Another common thing that we do in the bag of words model is words like it and is and stuff that doesn't have a whole lot of meaning outside of the context, we just throw out. Okay, we call those stop words. They're just really common words that just don't add a whole bunch of meaning. So we just throw them out in our analysis. Okay, anyway, this is how it would work for a document classifier. Okay, the document classifier requires something that we would call a lexicon that has probabilities for every word. Okay, a real lexicon would probably have between a vocabulary of maybe 10,000 to 80,000 words. And you would have to define a lexicon with probabilities for all of these different document possible categories. Okay. The sum of all of the word probabilities would add up to 1. And so anyway, here I've created this really, really, really simple and exaggerated lexicon for 2 possible classes with a total of 8 words in our vocabulary. So this is a little bit ridiculous, but I've done this way because I think it'll be easier to see and understand. And then you can just generalize to say, thousands of words and maybe hundreds of categories. Okay. So we're going to say when somebody writes a document or something, this thing that they're writing, it could be they're talking about fairy tales or they're talking about chess, the board game. And the words that we might see are words like king, queen, princess, knight, rook, good, evil, and bored. And so if it's a fairy tale, okay, king frequently appears in fairy tales, queens appear in fairy tales, princesses appear in fairy tales, and so do knights. Okay. But the word rook, all right, that's not going to appear as much in fairy tales. Okay. Good and evil, those might appear with regularity in a fairy tale story. The word bored, however, we'll say is unlikely to appear in a fairy tale, and so we'll give it a probability of 0.01. Okay. When we're talking about chess, though, okay, king and queen will have higher probabilities, 0.2, 0.2. Okay. Talking about a princess in chess, pretty low probability, 0.01. Okay. Knight, 0.15. Rook is a piece in chess, so we'll put 0.2. Good, like maybe somebody made a good move, 0.13. We'll put a high probability. Okay, the word evil, though, is unlikely to show up in a conversation about chess, I think. Okay. So we put assign a low probability there. And then the word bored, however, will appear with a decent amount of probability. So we'll put a word probability of 0.1. Okay. And so this is the lexicon that I've made up. in real life, you would probably have to, quote, train your lexicon by taking into scanning a whole bunch of known documents of known classes. So, you might go through newspapers and you say, I know these newspaper articles are already labeled. This article is about politics. This article is about sports. This article is about science or whatever. And you scan all of these things and you just kind of accumulate all of the different words that appear. Okay. And so the words about in the documents about politics, you just say, how many times does the word house appear? And how many times does the word, I don't know, whatever, this and that appear? And you just count them up and you get kind of approximate probabilities for each of those words. And you do it for all of the different things. And again, it's going to be a common practice to just throw out these super common words like is, the, to, a, because they're not going to help us understand, context or meaning from the document. Okay. All right. Let's, oh, this got a little bit messed up. Okay. Let's say we see this sentence. This is our document that we want to classify. The evil queen sent the evil knight to capture the princess. Okay. This is not very good writing here, but okay. Based on this, is this a story or is this sentence coming from a fairy tale or something about chess? Okay. And our clues here is we read this and we go, yeah, that's probably not about chess because we're talking about princess, right? If it was just kind of like knight captures queen, yeah, that could be chess. But here we're saying evil queen sent the evil knight to capture the princess. So we go through and we look at the word counts for the words that appear in our dictionary or our lexicon. So queen appears once, princess appears once, knight appears once, evil appears twice. And so we say, okay, what is the probability, the likelihood that this sentence came from fairy tale? So we say, all right, if it came from fairy tale, what's the probability for queen? 0.2 once. Okay. What's the probability for fairy princess if it came from a fairy tale? 0.25. Probability for knight is 0.2. Probability for evil is 0.11, and that appears twice. And so the likelihood for these words, given that it was fairy tale, is, the product of that 0.2, 0.25, 0.2, 0.11 squared, and you get 0.000121. Okay, not a huge number, okay, but 0.000121. Okay, compare that to if we said it was from chess. Okay, for chess, queen for chess is 0.2, princess for chess is only 0.01, knight for chess is 0.15, and evil for chess is 0.01. So you have 0.2 times 0.01 times 0.15 times 0.01 squared, and you get 0.00000003. Okay, so really even much, much, much smaller probability. So here it was 0.000121, and here it's 0.00000003. And so you can calculate the kind of marginal probability. You do, let's say our prior probabilities is it was a toss-up, 50% chess, 50% fairy tale. Okay. So I do, this times 0.5 and then the likelihood times 0.5. We get this number. And then I calculate my probabilities. And so my posterior probability that it was a fairy tale is like 0.999 versus 0.000247. So this is 99.98% that it was a fairy tale, and this is 0.0002. So like 0.02, well, 2 in 10,000, maybe, yeah, 1 in 4,000 chance that it was something about chess. Given our probabilities. And I think looking at that sentence, we would be in agreement that it was unlikely to be about chess. Okay. Last view quiz answer is the letter D. D as in dog. And we'll end there. That's an application of the naive Bayes classifier. Could be used for document classification or any kind of other situation where you need to do a classification thing and figuring out the covariances is very difficult. Okay, we'll go ahead and wrap up there. Have a good weekend. Good luck as you study. We'll see what the school says, and I'll keep you posted. Again, if I don't hear anything by 8 a.m., I guess a practical deadline will be like 7:50, 7:50 the morning of Monday. We'll go. Okay. We'll go forward. Okay. So okay, we'll see you guys. Well, we'll see. We'll see what happens. Okay. Have a great weekend.